So welcome and good morning. So it's a pleasure and honor to be here and a pleasure to go in this workshop. And I thought in the very beginning it might be good to have a slightly not so technical presentation. So what I try to do in my talk is show you some basics of what I call latent semantic variable models, and also show you a range of applications for these models. Okay, so that's more the emphasis here, and there will be some follow-up presentations by Michael Titterington and by Ray Buntine that will cover, I think, more in depth on a technical level some of these subjects. So basically, what I'll talk about is a technique called latent semantic indexing and how it relates to information retrieval, a probabilistic version of that technique called probabilistic latent semantic indexing. I will talk a little bit, that might be interesting, in particular for the more narrow topic of the workshop, about how these semantic features that are extracted with these techniques can be used for text categorization. And then I'll talk briefly about a probabilistic version of Heinrich's HITS algorithm for web search and collaborative search. Okay, so latent structure, the way I will be using that term here, I'll be referring to that term as not in its full generality, but rather in a more specific sense. So I'm interested here in matrices that typically encode co-occurrence data, co-occurrence counts of events. Okay, so we will have matrices like this, an n by m matrix. And you will see some examples in a minute. And basically, with these large, typically very sparse matrices, there are all kinds of problems. I mean, they're too large, they're too complicated, they're missing entries, they're noisy entries. And there's, in general, we feel there might be some underlying structure which we don't see, on the surface, but just looking at these matrices. So what we're looking for somehow then is a simpler way, in a sense, to explain these entries in a matrix by using a model, and then also uncover what you might want to call a latent structure of the data. Okay, so that's the general goal here. And in particular, the types of methods that I will talk about are closely related to matrix decomposition techniques. So what I call matrix decomposition here is simply a factorization of a matrix. So say we have a matrix A. We want to approximate it by some matrix A hat, which can be written as a product of two matrices L and R. And these two matrices are typically constrained to be thin. So, if A is an n by m matrix, L might just be an n by q. So, a very thin matrix, and then we might have R, and we might have a diagonal matrix in between. And the idea is, right, to find these types of factorizations of matrices, and I'll try to explain how that relates to something like latent structure in a certain sense. Okay, so that's just a brief introduction of where I'm going. Okay, so let me now talk a little bit about a particular application, information retrieval, and this technique called latent semantic indexing, which was developed in the late 90s. So first of all, try to convince you that information search is important. Well, we all know that, right? In order to access information, the most popular way of doing that is to use a little box like that, a little box, a button. And then, we have all the knowledge of the world out there, and then certainly, somehow, magically, we will get access to that knowledge. And indeed, there's some magic, other names here like Google. And if you look, on the web, there's no website, basically, that doesn't have a search functionality, right? You go to CNN or Medline Plus, and, wherever you go, everywhere you see, basically, a search box like that. Okay, so apparently, it's an interesting problem, so it would be good if we could somehow improve search, right? So that's just in terms of the relevance of the problem. But really, somehow, of course, we all know that, and we know that because very often things don't work out the way we expect them to work out, that, it's really this idea that we can identify relevant documents just based on, a very short, ambiguous, and incomplete query is a bit of, we have very high expectations here. And but nevertheless, it's very popular. I have some numbers here, of how many people use it, and but we all know that. I mean, we certainly use, I would assume, search on the web, for instance, every day, and more people use it in their professional life and their personal life. Okay, now let me try to show how a matrix comes into play here to connect it with what I said first on my first two slides. Okay, so the typical matrix we're talking about here is called a document term matrix or term document matrix, depending on which way you transpose the matrix. And so we have a document here, we have a term, and then what we typically do in many information retrieval applications, we reduce the data to this matrix, which as an entry has just a frequency count of how often a particular word occurred in a document. Okay. So then we can take a particular row of this matrix, and then we can use that basically as a representation of a particular document. Okay? So if we have many terms, say we have tens of thousands of terms, it will be a very high dimension of representation for each of these documents. And of course, there will be lots of zeros and so on and so forth. And a lot of information retrieval techniques are based on these document representations just by term frequencies, right? And the reason why it works, at least to some extent, is that indeed in the words that occur in a document are good indicators in some sense, right, of whether a document could be relevant to a particular query. So that a lot of the deeper, maybe, syntactic analysis and linguistic analysis is very often not necessary on a surface level to find out whether a document could be relevant or not. Of course, that depends on what you want. If you want question answering systems, then you need to look more into the structure of sentences and things like that. Okay, and then in practice, what people often do is they multiply these entries by some smart term weighting, like IDF weighting, and then you get this TF IDF and things like that, and that is used in a typical retrieval system. Okay, now how does this matrix look like that we get? Well, I can't show you a typical matrix here, but I can show you hundreds of a millionth of a typical matrix here, and that's basically what it looks like. Right, so it's a big ocean of zeros, and then there's some islands of non-zeros, right? And it's big. Okay, so the assumptions I made here are basically we have a million document, about 100,000 terms in our vocabulary, and a degree of sparseness of about 0.1%, which means every document uses 100 of the terms in the vocabulary, which, if you look at news and shorter documents, is a reasonable assumption. Okay. So this is how this matrix looks like, and clearly, we don't want to look at that beast, that very sparse matrix, but really we feel perhaps that this matrix should have some interesting structure that we can reveal. Okay, now first of all, what does it mean that this matrix has so many zeros, right? So this is a problem, really. It's not just that it's almost everywhere empty and very sparse, but going back to the application that I was talking about in search, there is a problem called the vocabulary mismatch problem. And that is that if we look at a particular document and look at the actual content of the document, there are many ways to express certain concepts and certain facts, right, by using different types of words. So, but typically in a document, we will use one particular word. So there will only be a subset of the words that could be used are actually used, and that's a decision based on style or personal preferences or just the precision in language, And that leads to this vocabulary mismatch problem, which means that, very often we might use certain terms to query for a document, but then the document might not contain these exact terms, but might contain other terms, because the author has decided, to use other terms, okay? And of course, in our matrix, that means, there are just so many zeros where, in principle, there could be non-zeros if the author would have chosen other words, but he or she didn't, okay? So, and here, just to give you some idea, right, we know that we might have a query for this document here, labor, immigrants, Germany, and then we're happy because all of the three terms occur, and we can see that that is relevant. But as soon as we start varying the query, right, say to the point where something like German green card, then none of the terms that we use are actually in the document, although that might actually be a good match with what this particular CNN news document here talks about. Okay, so what we'd like to accomplish is to get some robustness with respect to these variations in the queries. Okay, so that we're not getting a vastly different answer every time, and in particular also that we find relevant documents even if we don't use the specific terms. Okay, so what are the main challenges here? The compactness, so a typical query consists of about 2.5 terms, right? We all know that. That certainly agrees with my own statistics. There's a great variability in language. There's synonyms, semantically related terms, and so on and so forth. There's a lot of ambiguity. So, for instance, terms with multiple meanings. To give you an example, if you query for, say, Ulysses, at the time I did this at Google, you find information about Ulysses, a space probe, about James Joyce's book, and then about Ulysses S. Grant, who is a general in the American Civil War. Okay, and then there's also a question, of course, of quality and authority, which is important in the web context for something like Google. Okay, so now I talk about a technique that can somehow help to address some of these challenges. Okay, and that goes back, as I said, to the late 80s, early 90s, when people invented this technique called latent semantic analysis or latent semantic indexing. And the idea is that we take this huge matrix and we perform a low-rank approximation of that matrix and, say, reduce it down, approximate it by a matrix perhaps of rank somewhere between 100 and 300, just to give you kind of a rough number. And the general idea behind this was that, we would map documents and terms by computing this low-rank approximation, effectively map them to some low-dimensional space, 100 to 300-dimensional space, in which hopefully, by, for instance, computing inner products in that space, we would uncover some more semantic relations between documents and words, in the sense, for instance, that two terms that are semantically very closely related would have very similar representations in that space, and then so also looking at documents that contain semantically related terms, although perhaps not exactly the same terms, that will show up basically in the inner product. Because if we just use the terms, of course, and two documents use different terms, then the inner product will just be zero, kind of in the original space. So that's basically the idea, and the hope was that that space somehow corresponds to what they call the latent semantic space. Okay, so that's kind of the hope, that it reveals something of the underlying word meaning and underlying concepts, really. Okay, and so the technique that is used here, that was proposed by this group of people at Belcore, is a singular value decomposition. So I'm sure we all know this, but let me just briefly walk through this. So we have a matrix A, and an SVD is a decomposition into a matrix U, sigma, and V transposed, such that these are basically the dimensionalities of these matrices. So we have a number K here that I'll explain later. And these matrices have orthonormal columns. Okay, so, and then the sigma matrix, which contains the singular values, is diagonal. And we will choose a particular permutations that make sure that they are ordered according to size. Okay, and then this number K is the rank of the matrix A, which is bounded by the minimum of n or m, but can be smaller than that, of course. Okay, so the singular value decomposition, of course, has nice properties, and in particular, we will basically see if we ask ourselves, okay, we want to approximate the original matrix, say the term document matrix, by a long-rank approximation, and we specify some norm here. Say we use the Frobenius norm, which means we look at the difference of the original matrix and the approximation, and we just basically look at the sum of squares of the entries of that difference matrix, and we minimize that. Then it's well known that the solution can be computed directly or read off from the SVD, and the only thing we have to do is, if the matrix is of rank K, to basically delete the smallest singular values, set them to 0, and then only keep some number Q if we want a rank Q approximation, right? And we just keep the U and V transpose matrices. And then that is the solution to this problem. Okay? So that's, in fact, what people have proposed in this latent semantic analysis. And so it can be summarized as follows, right? We have this term document matrix. So looking at the rows correspond to individual documents, the columns to terms. And then we decompose it using SVD. And then we kind of get representations for our terms on this side, like in this case, what was Q before is K now, so we get K-dimensional representations of the terms, k-dimensional representations of the documents. And basically, we can do all kinds of things, compute document similarity using now these low-dimensional representations. And we can, if we have a new document or a query, we can what's called fold it in and compute the representation also in this latent space. Okay, so and then here's just a little picture to show you. I don't want to go much more into depth here for latent semantic analysis, kind of what the idea behind this is. So here we have two terms like laptop and portable, and two documents. Document 1 uses the term laptop. Document 3 uses the term portable, and they're the corresponding document vectors are orthogonal to one another. And the idea is, or the hope is that if we map it to this latent semantic space, say document 1 and 3 will be closer to one another, and basically, and you will also see that in terms of the terms, laptop and portable will be very close to one another in the semantic space. So that now, for instance, document 1 and 3 are more similar to one another than to document 2. Okay, I don't want to go into much more into depth here, and rather talk about a probabilistic version of this, and then talk a little bit about, when I talk about experimental results, also mention kind of, how well LSA actually works and how it compares to probabilistic techniques. Okay, so let me now talk about probabilistic latent semantic indexing. Okay, so, and what I'd like to do first as a motivation here for moving to talk about probabilistic models now, I'd like to pose the problem of information search as some type of inference problem, and I'd like to motivate it in the following way. Imagine that we have a document like this, which is broken up into terms or phrases, which is also in another context often called a bag of words representation, and we have a query like this one here, which contains certain terms that are in the document and others that are not in the document. Like in this case, China and trade, for instance, are not do not occur in the document. Then we could ask the question, given the context, how probable is it that a term like China or trade might occur in that context? Okay, so like going more now into probabilistic modeling. Okay, so I see a particular context, and I try to figure out, well, how probable is it that in that context other terms might occur? And very practically, you could just think of it in the following way that, some of the terms have been hidden, haven't been shown to you, and you're now speculating about what these terms could be. I tell you one of the terms was deleted, and you have to predict it. That's the kind of the game we're playing here. Okay, so you try to figure out, well, looking at maybe you see Beijing and things like that, that might increase your probability that China could also occur in that context, right? That it might be more probable, say, than another term like Russia or something. Okay, so a good model might be one that assigns very high probability to a term like China here. And if we can compute these probabilities, right, then we can do all kinds of things. And just to give you an idea where we're going here is particularly we can perform something like document expansion, where we can say, well, look, these terms do not explicitly occur in the document, but somehow we can add some terms that nevertheless, based on the context, have very high probability. We can kind of add them to the index terms using some weight, perhaps, right? So, we're imagining new relevant words so that we can match documents with queries that contain terms that are not showing up in the document. Okay, and this is called, in IR, this has been called the language model paradigm in IR. So this was introduced around 98, 99, a couple of papers on that. And the idea is as follows. We say, well, RD introduce a binary random variable, say that models the relevance of a document D, and we have a query Q, and what we'd like to know is whether, given a particular query, a document D is relevant or not. And one way to look at this is then simply to apply Bayes' rule here. And so we will have two contributions here. The prior probability of relevance for a document, well, that is usually based on things like popularity of a document, or it's just a constant, dependent on the context. And then something that's written here, which is, in plain language, you could understand, or you could express as the probability of generating a particular query Q to ask for a relevant D. So given that we assume that the document is relevant, what's the probability to ask for that document with a particular query? Okay. And that's basically, okay, so the standard approach to that is to basically treat the query terms as a sample drawn from a relevant document. So basically, I mean, they're mods of different complexity here, but basically what we'd like to have is a model for each document that tells us how probable certain words are, and then we could just assume that a query is a sample generated from these words. Okay, so this is the language modeling paradigm again, to make that clear conceptually. So the idea is the user has some document in mind that is kind of the ideal relevant document, perhaps, or a relevant document, and from that the user generates a particular query, and then we'd like to reverse that process, basically. Okay, so what is now a naive approach for doing that? Well, we could just say, well, we just use the maximum likelihood estimate here. I mean, it's not even worth calling it that. It's basically, we could just use the count statistics, right, normalize, and then that's the probability to see a word in the document. So that just basically assigns, the relative frequencies to the words that actually occur. But then, of course, we have this problem that the terms that do not occur get a zero probability, and then, a query that contains a term that's not contained in the document will just get a score of 0. So the real question here is, in this estimation problem, is how can we bring in the other documents in the collection? Okay, so from a very practical point of view, the idea is not just to treat a document in isolation, but rather the whole collection, which is also encoded in this term document matrix, right? That encodes the whole document collection. And how can we bring that in to improve, to come up with better estimates of these document-specific language models, the probability of a certain word given a particular document? Okay, so that's the idea. And so this approach that we've been developing under the name probabilistic latent semantic analysis works like this. Okay, we have, again, document in terms. And now we introduce an intermediate layer, if you like, a bottleneck layer of so-called latent concepts. And what we try to do now, instead of learning directly probabilities of terms in documents, we learn the probability for each document to, if you like, participate in a particular concept, Z, and then the probability for each concept that concept is expressed, this latent concept is expressed by a particular term. Okay, so the idea is we might have a document here dealing with issues related to trade. Hopefully our model, once we fit our model, I'll talk about this in a second, we'll find a concept that might correspond to something like trade, and that might have very high probability to be expressed by terms like economic, imports, trade, and so on and so forth. Okay. So particularly, notice that these concept expression probabilities are estimated based on all documents that are dealing with a concept. So we're using the whole collection at that point to try to estimate these. And what we're doing here, in a way, is we'll see that on the next slide. Is basically a mixture model where we assume that each document is composed of a simple mixture of topics or concepts, and that's what we're trying to uncover here. Okay, and the nice thing, of course, is it's completely unsupervised, just based on the co-occurrences of words. Okay, and here is what I've just described in this little picture. Is also very simple as an algebraic expression, how this model looks like. So the probability of a word given document is a simple mixture here of a Z. So this is our document language model. We have these latent concepts, and then we have these concept expression probabilities and these document-specific mixture proportions. Right. Another way to look at this is to say that it's a convex combination of these concept expression probabilities. So every document, since these add up to 1 and they're non-negative, right, forms a convex combination. If we think of P of W given Z as a vector, forms a convex combination of these vectors. Okay, and so we're trying to find kind of a basis or a set of vectors here so that by looking at a particular convex combination for each document of these vectors, we achieve a good predictive model somehow. Okay, and so these we have to learn in a model fitting stage, right? And so let's see how and why that might relate to matrix decomposition. So there's basically a way to take that model, P of W given D, this conditional model, and just make it into a joint model by thinking of D also as a random variable. So we could just give it a prior probability for a document. Say it could just be uniform, or it could be the length of the document, actually, when we have to estimate that parameter. But basically, we can reparameterize it in a symmetric form, like written here, as a sum over these this latent variable Z, prior probability of Z, and then the probability of D given Z and W given Z. So this also reveals this conditional independence assumption that we're making here. And if we do that, then we can actually see that by thinking of these as matrices, right, and the P of Z as kind of a diagonal matrix, that what we really get is, if we rewrite it in matrix notation, we get something that looks very similar to an SVD. Of course, it's not an SVD in the sense that we don't have orthonormality of the columns and things like that, but just in terms of a decomposition. Of course, what's different here, for instance, is that in contrast to LSA or SVD, all of the entries here, for instance, are non-negative, and they are not normalized with respect to the L2 norm, but rather with respect to the 1 norm. So they add up. The entries of all the columns of these things add up to 1. Okay, and there's a relation to non-negative matrix factorization that I'm sure Ray Bantine will explore after lunch today. Okay. We can also look at it as a graphical model, and then the way I'd like to explain this is that there are 3 levels. There's an occurrence of an individual word in a document, there's a single document, and then there's the whole document collection, and we can look at first an occurrence of a particular word that we observe. We associate with every occurrence a latent variable that sort of indicates what the underlying concept is of that particular word occurrence. For a particular document, we try to estimate a parameter that specifies a probability here of what the probability of a particular concept is given a particular document. Okay, and then as far as the collection goes, for a particular concept, we estimate these expression probabilities. Okay, so there are things that are every occurrence of a word has this latent variable associated with it. This is shared by all word occurrences in a particular document, and this here is shared by all documents in the collection, basically. Okay, and so now, how do we actually estimate these parameters? Well, the simple thing we can do is to perform something like maximum likelihood estimation, say. And so we write down the log likelihood here. So, we look at all of our document word pairs, look at the observed frequencies, and then the probability of our model, or the log probability of our model. And this could be written as this mixture over the latent variable C. Okay, so this is the log likelihood that we're getting here. And now we just try to maximize that with respect to theta and pi. And of course, this in general turns out to be a non-convex optimization problem. But one way to come up with a proximate solution is the expectation maximization algorithm. I don't want to go too much into depth here because I assume most of you are familiar with that. And if you do that, basically, so this is, of course, standard statistical technique. Then you then have 2 steps. In the E step, what you do is you compute the posterior probability, of course, of your latent variable. And what that means in that particular case here is that you look at every word occurrence in a particular document, every DW pair, for those pairs that actually occurred. For the others, you don't have to compute it. So if you have this big matrix, you only have to do this for those entries that are non-zero. And you do that, and that's basically the probability that the occurrence of a particular term in a document can be explained, if you like, by this particular concept. And you can see it's a very simple equation here. And then in the M step, you just use these completed statistics, if you like, the expectation of the sufficient statistics, and use that to estimate these probabilities. So what you get then is basically over here, how often is a particular term associated with a particular concept. You just count that, or you add up these fractions. And over here, how often is a particular document associated with a particular concept. And then you just normalize so that these things really become probabilities. Okay, and then of course what you do is you reiterate, and you do that for a while until you get close to convergence, or you have some stopping criterion maybe where you stop the argument. Okay, I don't want to talk a lot about the derivation here really, but one way to do this is to, you've probably seen this, to introduce this variational distribution, apply Jensen's inequality. The only thing I want to say here is that what we've been doing actually to be able to improve the generalization performance of EM and to avoid overfitting is we've used this what we call tempered version of EM, where if you look at this derivation with this variational Q distribution, you artificially, so you have this term here, which is the expected complete data log likelihood, and you have this entropy term here, is that you artificially increase this entropy term. And so kind of you try to make these distributions, and since this is just a distribution over a finite state space, you just try to make it more uniform, basically, by making beta smaller. Okay, so this is, there are better ways of doing that. Again, probably Ray Bunton will talk about more Bayesian approaches to doing inference with these types of models. But this is something that in practice gives you a good compromise in terms of the efficiency of the whole procedure stays the same. But you have some examples here where you see, for instance, you do EM and you do whatever 20-something iterations, and then if you don't stop there by using some maybe holdout data set to do early stopping, the generalization performance goes up again, right? And if you introduce this kind of inverse temperature parameter for different settings, you can see that this is just a perplexity number here. So the log likelihood on the test set, you can get much better results by doing that. Yeah.
So is this a way of smoothing the likelihood?
It's a way of, so basically what you do is you use that objective function as a basis for EM. So if in the end step, you're just optimizing basically the same function with these variational Q functions. But when you compute in the E step, when you compute these Q distributions, they are no longer the posteriors, but they become biased towards being more uniform, basically. Right. This is also, people do this for instance, in speech recognition. It's very often you make certain independence assumptions, right, that are not true, and then you're adding up evidence, which means you're multiplying these probabilities that are not really independent, and then you get typically overconfident in your estimates for your posterior probability. And it's just a very, I'm not saying that this is something you should do, but actually in practice often useful. One way is just to discount for that. Double counting of evidence is just to rescale, right, and say, I don't know, if you think about things like more naive Bayes models or something like that, right? You have 50 observations, and now you're 100% sure it belongs to this class, right? But you made independence assumption that's wrong, and maybe you shouldn't talk about 50 independent observations. Maybe there are only effectively 10, let's say, right? So if you know that, then you could just basically rescale that. but of course, the right thing to really do this is a more Bayesian approach, where you introduce priors on your parameters, say, and then use that to avoid overfitting. And I'll come back to that just briefly. So anyway, looking at the EM algorithm is really simple algorithm. I mean, the model is simple, the algorithm is really simple. And here's now an example of the types of things that you find. So in this picture that I've drawn, what I'm showing here are basically these vectors. And what is that? Well, we have as many of these vectors as we have concepts. So I've shown 3 concepts here. And then each of these vectors will contain, for each term, a probability, which we have rescaled here to make them look nicer, and then ordered the terms according to their probability. Okay, so each concept, with each latent concept, we've associated these vector of what I call expression probabilities, right? And this is what you see here. So for instance, if you look at this particular, say, concept number 2 here, we would see that it corresponds to something, to a certain context where words like ship, boat, tanker, boat, ships, ferries, and so on and so forth have very high probability. So you see there a lot of words are grouped together here that are semantically closely related in the sense that they could be synonyms or near synonyms, or more like a tanker is a specific type of a ship, I guess. But there are also terms that often tend to co-occur, although they are not types of ships themselves, like sea and port. And of course, this simple algorithm is blind to whether it's a true synonym or whether it's just something that co-occurs in a particular context. And then there's also things that are very specific to this data set of AP News, which at the time there was this accident with Exxon Valdez, so that, this also is associated with ships and tankers and boats in general here, because this was just represented in the data set. But you can see that these concepts kind of tend to make sense, or they capture something that you could claim is at least not completely random. I mean, showing these things is always, there are also some concepts that are typically that are not so easy to interpret. But there's some very often that makes sense also to humans if you look at it in that particular visualization here. Okay, here's another example. This was a concept extracted from 12,000 articles from Science magazine. And you can see things like over here, right? Sequences, genome, DNA, chromosome, and so on and so forth. Things related to genetics, down there. You can also see things like this one here, which has all kinds of things doing with time and years, year, and then all kinds of numbers, million, billion, ago, age. Yeah. So so these things also statistically are kind of grouped together in one concept. Okay, so this is how it looks if you visualize this. Now I have a little bit on a more quantitative evaluation, experimental evaluation here. So the most interesting one is the one on a TREC data set. This is TREC 3, and what you can see here, this is it's hard to see here, but this is relative gain in average precision. So that's basically is a standard way to evaluate how good a ranking is in retrieval. And you can actually see that LSA, in that case, doesn't really give any improvement for these smaller data sets that have been tested on before. We see some moderate improvement, but that with this probabilistic version of LSA that I've shown you here, gives you much better results. Typically, on TREC, we have like a relative improvement gain of about 80%, and with some of these other collections, it's higher than that. So that basically says that, whether we can really make sense of these concepts or not, they capture interesting regularity that helps to improve search. Okay, so the words that we associate with documents based on a model like that seem to be useful to address this vocabulary mismatch problem. Okay, and we've also have a number of live implementations of the system, which has been commercialized to And one of our customers is, for instance, Medline Plus. Now, that's not so much of an issue perhaps in Europe, but this is a very popular health portal in the U.S., which is sponsored by the National Library of Medicine. Okay. All right.
Basically,
yes.
your application was improving the search with.
Yes. Right. So there are all kinds of vocabulary mismatch problems here, also in the sense that there are some of the documents have been written by doctors and medical experts, and then they're just ordinary people going there, and they use different terms very often than the ones used in the literature, right? And we have interesting examples really where you would learn that these things are kind of synonyms, right? I'll say a Latin, right, technical term and a term that some average customer would use. So so their content team, they've evaluated the system on, I think, 1,000 queries or so towards like a standard system, right? And they found that it has increased the performance quite a bit. And I don't have the hit rates also. The usage of that health portal has gone up a bit, but also there have been other changes. For instance, we can also, I don't think I have this here. We can also do things like if there are ambiguous queries, we can actually group the results according to the different meanings of particular terms, and a number of things we can do here.
Did you index the whole Medline?
It's not the Medline the Medline document database that like a doctor or a researcher would subscribe to. These are documents that have been put together by the National Library of Medicine, and then some outside references. So I think it's about 100,000 documents total. So it's not the Medline data set.
Are these concepts, these latent concepts, somehow visible for the users, or are they just kind of hidden for the server?
Yeah, that's what I was saying. Is if you enter a very ambiguous query,
so you get this
right,
clusters.
then you can make that explicit. I mean, there are a lot of things you can do. In general, you don't want to confuse the average user by having a too complicated, very fancy-looking output, and then they have no idea what to do with that. So that, I mean, users have very very constrained expectations, right? I enter a query, I get the list of documents, and at the top of that list is exactly what I want. I mean, that's basic. And so, but one thing you can do is really, I have an example actually at the end, something like bleeding, for instance, right? There are all types of bleeding, and instead of mixing all the documents that have to do with potential bleeding problems, in one list, you could just separate it, and then people can zoom in and can say, yeah, that's what I meant. And then they, can find information more in a more focused way. Okay, so what I'd like to mention just here, because I assume that Ray will elaborate on that, is a model called Latent Dirichlet Allocation Model, which, in my view of the world at least, is a generalization of this PLSA in a relatively straightforward way. And the way you can generalize PLSA as the following. Maybe I just show you the whole slide here. Is by introducing a distribution. So the probability over the concepts for a particular document. This was a set of parameters that we estimated using EM. You can also make that now a distribution. You can say a particular document, right? What you do for a particular document is you draw, according to some distribution, you draw these mixing weights. Okay, and they have some parameter pi here. And say that parameter has now a distribution with some hyperparameter alpha. And for instance, you can use there something like a Dirichlet density, okay, which basically says you extend this model to make it a generative model. You say, well, for each document, you sample according to this Dirichlet distribution, you sample these mixing weights, and then you have these guys over here, these parameters, and then you combine them, and and that gives then here you see now actually that you multiply the probabilities of all the word occurrences in the document, and so you get you get a true generative model. right, which you can obtain. So the probability of all the words in a particular document you can then obtain by marginalizing out this pi parameter here. Again, where you have the Dirichlet distribution over there. Okay, so this has several advantages. One is, if I give you a new document and you want to assign a new probability to all the occurrences of the words in this document, you couldn't do that in PLSA because it is kind of, you just look at this matrix, and if a document is not included there, then somehow you have no idea what the probability could be. Sort of the sample space is really just all the possible entries of the matrix, and these are just counts over a fixed sample space. And here you can do that, and then also, of course, here you get other benefits of a more Bayesian type of approach, which means you don't have to do maximum likelihood estimation for these pi parameters, not even map, but you can try to really approximate the fully Bayesian approach here, doing say variational inference as proposed by Bly and others, and there've been a couple of follow-up papers on that. Okay, so this is a more recent development, and that has shown to improve the generalization performance of the models quite a bit. Okay, there's some work that you can look at if you would care to download my presentation some point later after the workshop. Okay, so how am I doing time-wise? Still have some time.
Like 15 minutes.
Okay. So the rest is really now, doesn't take that much of a time. What I'd like to show you now is different variations around this idea. So the first thing is, if you extract these concepts, right, shouldn't these concepts somehow also help you in a supervised learning task, for instance, in text categorization, right? And here, most text categorization algorithms like naive Bayes and k-nearest neighbors, and also AdaBoost, like the text booster system, or SVMs, they usually are based on just the term-based representation, right? But the question is, if I can extract these nice concepts, somehow can I exploit this also to improve text categorization? And what we did here, this is a Sigar paper from you'll see on the next slide, the Sigar paper from 2003, is basically combine AdaBoost, two different versions of AdaBoost, where we used weak learners. The set of our hypotheses consisted of two different type of simple hypothesis. One is just an indicator function for term features. So it's whatever, a -1 if the term is not present in a document, otherwise it's a 1. And the other one, what we did is we would run this probabilistic latent semantic analysis over the whole document collection, and that would give us these concept probabilities for every document, right? And we would take that as a kind of representation for the document in that concept space somehow. And we just, used very simple indicator functions here where we had some threshold that we also optimized over beta, and where we said, well, if the probability is below that, right, then somehow the document is not on that concept, so it's a -1, otherwise it's a 1. Okay, so we have these very simple functions, and what we do now is we combine them using AdaBoost. Okay, there's just standard AdaBoost process. And just to show you that experimentally, you can gain by doing that. So this is on the, I don't want to go too much into the details of the experimental setup, but this is the well-known Reuters 21,000 something data set. And, since this is a SIG-IR paper, we used 1,000 different metrics and 1,000 different setups and who knows what. But this is just showing improvements in terms of F1 measure and the average precision for micro and macro average. So it depends on how you treat the different weight the different categories, and you see that you get some improvement that's very consistent. That's not, it's not revolutionary, but it's a solid improvement across the board. And also we looked at a more interesting data set. This now is a subset of the Medline collection, 50,000 something data sets, this Oshumet. data set, and we see here improvements in average precision around relative improvements of about 5%, about 2% in absolute numbers, 2.5, and also in terms of the F1 measure. And it's actually interesting also, if I don't have a figure here on that, but if you look at how boosting behaves, it first picks individual terms typically that are very discriminative for a particular category. And then it starts looking more at the concepts. And then at the very end, it typically goes back to picking individual words and rewriting things again. So it's kind of interesting also to see how these things are combined during the boosting process. But again, this is yes.
I just wanted to add, it's kind of related experiments. I mean, this might be more sophisticated in this probabilistic sense, but just by expanding or putting together words or replacing the words by the synonyms for WordNet, more or less, you get similar performance.
I can imagine.
It's the same experience. So some concepts are more like, some features are more like concepts, some are more like words. So it depends on the data set.
Yeah, I mean, and there have been other, of course, similar approaches in that direction. So I had another paper on actually deriving a kernel from this PLSA model and then combining it with this Fisher kernel idea. And then there's also been work on, say, semantic kernels based on LSA and others in John Shaw Taylor's group. Okay, but that's just to try to convince you that these unsupervised methods, and the types of structures that they discover are also helpful. To what extent depends on the specific data set, but in general also helpful in a supervised learning application. Of course, the PLSA you can run also over larger data sets that are unlabeled. So if only a small portion of your data set is actually labeled in a supervised learning setting, you can learn your statistical model from perhaps a larger data set and take advantage of the unlabeled data as well. Okay, let me now briefly talk about another application of these types of methods, and that is called probabilistic hits. Hits is referring here to a well-known algorithm by John Kleinberg. So for those of you who are a little bit familiar with that, right, there's the PageRank algorithm that the Google people developed. And then there's this, I think it's called hypertext-induced topic search. So it's called HITS by Kleinberg. And it's based on this idea of authorities and hops and computing authority and hop scores. And what we've done here is we've used a similar model, actually, a probabilistic model for web graphs. And it's really very simple. It's the same model as before, basically, but only applied to directed graph, which represents the link structure of the web, or part of the web. Okay? And it works as follows. We try to come up with a model to estimate or to predict, whether there could be a link from some source page to a target page from S to T. And the way, we model this is that we split this up. We introduce these latent kind of web communities, and we say there's some probability that S will link as a source to another page in that community, and then the probability that T will be a target page for a page in that community. Okay, so it's the same type of decomposition. It's exactly the same. And so that's the idea here, right? So you have the source and the targets. Think of it as a bipartite graph. Of course, you might have the same page on both sides, since there might be incoming and outgoing links. And then, we have these source nodes. We have these probabilities on the left, and then we have these P of T incoming link on the right. And if we run now this machinery, right, something that we basically get is a decomposition of the graph, so that we can think of it as being superimposed of sparser graphs, right? Or another way you could think of it is look at, for each link, you can compute the probability that that link is associated with a particular community, and you can give that a particular color, right? Then there will be some links that have a much higher posterior probability to be associated with a particular community, and others will have a probability for another community. So what you get then is sort of, this is just an artificial example here, right? But you pick out these community graphs, and kind of in the whole web graph is just a superimposition of all of these graphs, right? That's kind of the idea. And and then you can also combine this with in a very nice way with the text that you find, say, on a web page. Okay, so you can now say, well, what that z variable should model is really both. It should model things that are expressed on the word level, something like a concept, but also you would think that these communities also evolve around certain topics, right? So that they can also be somehow, it's related to the content, and the content is not just completely independent of, how pages are linked to one another. And now you can basically, have this joint model. So there's a particular page, say, has a certain probability to belong to such a web community, and then there are certain probabilities that on a page, on such a source page, certain terms occur, and then certain links to other target pages occur. Okay, so you can have this type of a joint model here. And just to give you some idea of what you can do with this, coming back to this Ulysses example. So what we did here, just as an illustration, we used the query Ulysses, submitted this at the time to Alta Vista, and we built a graph of, I think it was several thousand, 10,000, what's called a context graph. Okay, so you take the highest ranked results and you build a little graph around it, and then we applied this decomposition technique to this subgraph of the web. Okay, and you can see that, and these are now the terms that show up in the communities, and these are on the target side, the links. Okay, the source side is less interesting usually. The target side is typically, this is where people are pointing to, right? And you can see here you have this space probe thing, right? You see it here with NASA and Solar and Mission and ESA, and you also see the web pages relating to that. And here you have Ulysses as Grant and war and Civil War, and you have the corresponding pages. And over here is a little bit mixed, but you see you have Joyce and teachers. So this is resources having to do with James Joyce. So you can see that basically, this big mess of superimposed all kinds of different topics, you're able to untangle that using these types of decomposition methods. Okay, so then before my time runs out, so there's also some literature on that. Let me close by showing you another application, and it's again same idea with a little extension in collaborative filtering. Okay, so here we are faced with the following situation. We have a typical user like this one here, and we observe some user ratings, right, which we collect into a profile. So say that user tells us, yeah, I really like that movie, I really didn't like that movie, and so on and so forth. So we built this profile, and now the question is, right, say, we are a DVD rental company, and we ask ourselves, is that person perhaps interested in renting a particular movie, or or buying a particular movie, or how would that person rate a particular movie, right? But the way we want to do that, though, is not based on particular properties of